Welcome again. Today we look at topic 20.3 for IB Chemistry HL, isomerism. Isomers refer to molecules that have the same molecular formula but different arrangements. This arrangement could be a simple structural arrangement, like in the case of the structural isomerism shown between molecules of pentane, or it can refer to different spatial arrangements. This type of arrangement is stereoisomerism. Today, we focus on two types of stereoisomerism. Configurational, focusing specifically on cis-trans isomerism today, where optical isomerism is covered in another lesson, and also on conformational isomerism. Let's take a quick look first, though, at an example of structural isomerism. And here we can see two structural isomers. The first one, C5H12 in a straight chain, is pentane, and the second, 2,2-dimethylpropane, has the same molecular formula, C5H12. The structural arrangement makes it a structural isomer of pentane. Now let's focus on stereoisomerism, which can be configurational or conformational. Here we see a molecular model of the molecule ethene, C2H6. And here we can see that an equilibrium exists between these two conformations. Here you can see the two hydrogens of this carbon line up, and the two back hydrogens also line up, with all of the hydrogens overlapping with each other, or eclipsing or blocking each other. In this case, there is a staggering of the hydrogens on each carbon, and if you looked at the molecule from this direction, you would be able to see all 6 hydrogens. This is referred to as the staggered conformation, and this the eclipsed conformation. And this is the notation that is used to represent the eclipsed conformation and the staggered conformation. Typically, both of these exist in equal amounts in a mixture of ethene. Another type of conformational difference that can exist among molecules occurs because of ring strain and the torsion that is caused by 4 carbons or 3 carbons going into this type of ring structure, where the typical bond angle of 109.5 degrees that you find in CH4 methane is forced to become 90 degrees in C4 and 60 degrees in C3. This brings a lot of strain onto the ring, and with the strain it causes puckering, or the uplifting of some carbons above the plane and other carbons below the plane, giving rise to different conformations. An even better known example of this type of conformational isomerism is found in cyclohexane, with the classic chair and boat conformations, each having 6 carbons and 12 hydrogens. But here you can see that because of the puckering of the ring, carbons arrange themselves in different conformations. Yet another type of stereoisomerism is configurational isomerism. In this case, simple rotation about a bond is not possible or is unable to bring about a transformation from one isomer to another. So we no longer have different conformations, but we have different configurations. A very significant area of configurational isomerism is optical isomerism. But today, we will look at cis-trans isomerism, also referred to as EZ isomerism. Here in cis-trans isomerism, It's easy to see why this form, the cis form, gets its name, and why this, the trans or the E form, gets its name. If we placed an imaginary line through each molecule like this, then we observe that the two groups with the higher molecular mass are both located on this side of the molecule. Comparing this group with this group has the higher molecular mass, and comparing on this side, this with this one has the higher molecular mass. With both of these higher molecular mass groups located on the same side of the molecule, then this becomes the cis or the Z conformation. Over here with the trans or the E conformation, the opposite is the case, with the higher molecular mass group here and the higher molecular mass group here on the opposite side, higher when compared to this, and this higher when compared to this. On opposite sides, a trans form. The designation Z and E is in keeping with the Cahn-Ingold Pelog rules formulated in 1966. Here once again, we should be able to see why this is designated the Z conformation, because on this side of the molecule, Br, being much heavier than C2H5, has a higher priority, and on this side, CH3 has the higher priority compared to H, with the two higher priority groups located on this side of the molecule. Then this becomes the Z conformation, also known as the cis conformation. On this side, the higher priority groups are located in opposite corners of the molecule, giving rise to the trans conformation or the E conformation. It's important to remember that the priority of a group is designated based on its atomic number. Can you determine if this isomer is the E conformation or the Z conformation?